In a 40-mile-an-hour gale, dawn of a fatal day, and the wind begins to speak with a roar that no man can fail to hear. In a 40-mile-an-hour gale, the center span weaves like a ribbon in a swinging twist that you wouldn't believe possible unless you could see it as you do now. There's an automobile caught on the heaving roadway. The 11,000...
So we should get rolling it maybe. I guess you'd have seen this maybe in your high school physics classes or maybe in your career on campus here as well. The famous, infamous maybe, Tacoma Narrows Bridge, Tacoma, Washington, South Washington, South Puget Sound, I guess, Tacoma. And you can see actually there's wind blowing on the waves, and so what this was before the realization that wind interaction effects on flexible structures like aircraft wings and also very flexible structures like suspension bridges have some effect. And basically what this was I think a 30-mile-an-hour wind that was just constant and unrelenting. And the mechanism is that it's almost like a guitar string, is that you have air flowing over the bridge, both top and bottom. It divides as it goes over the bridge. And in the lee side, I guess, windward side, it splits and goes top and bottom. In the lee side, it comes off as vortices. And at certain Reynolds numbers, certain velocities, it will shed a vortex from the top of the bridge deck and then the bottom of the bridge deck, alternately splitting it up. And so it's like plucking a guitar string almost, in that if the frequency at which that occurs, boom, 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 is the same as the resonant frequency of the deck, then it puts it in motion, and the motion gets more and more extreme. And if the strength of the bridge is not big enough to resist that, then it pulls itself apart, which is basically what happened here. And so now that that's known, you can do something about it. You can put dampers on bridges. You can change the aerodynamics to change the resonant frequencies. You can make them stronger, which you don't want to do because it makes it heavier and more expensive to build. But you can figure out exactly how to make it so the resonant frequency of the bridge doesn't fit with this shedding frequency of these vortices in the downstream portion of it. And so that's one part. And so things like Davenport's lab at Western University now in London, Ontario, this world first lab at a time, plays a role in being able to evaluate the forces on structures and the frequency of those forces on structures. Okay, this is paused. Does the volume work on this?
I don't think we'll be able to evacuate.
It does. It's very faint. Maybe I'll turn it off. I can tell you exactly what's going on, so it doesn't overprint my lovely voice. So 380, competitor to the 747. The video we looked at on Monday, taking off from O'Hare, or was it Wednesday, was from a top deck of a 747 out of O'Hare. I think they've stopped production on A380s now. It was a very short-lived foray into the market. I guess they found the market wasn't really a big long-haul market with big jets. It's much more a market with regional jets, linking small hubs, which seems to be how things have grown. And things like the Dreamliner, the 787, which is carbon fiber, low weight, high efficiency, high fuel efficiency, and there's an Airbus equivalent of that, I don't remember what the number is, are the way of to go, with direct flights between more remote hubs rather than massive hubs. But anyway, this is testing the plane. I guess they just got on the plane. They're wearing parachutes, which is always if the flight crew get on your passenger jet wearing parachutes, you should probably worry, I suppose. But this is a flight test, and they're basically trying to take the plane close to the speed of sound, Mach 1. And they talk in the narrative about being 0.98. Then they hear a bang, and some things get shed from the plane, and they land it just fine. But as you get closer to the speed of sound, from what we know about, you're listening to me, you're hearing me at the speed of sound. So the energy from me, if you like, coming out of my mouth is traveling to you at that rate. If you happen to be moving at that rate, then the energy that comes out can't get away from me. And so what happens at the speed of sound and beyond is that you get this Mach cone around the plane. It traps all of the energy that you're using to push through the air, and you put big stresses on the structure as a result. And in this particular case, they landed just safely, just fine, I guess, without any problem. There was a bang as they're traveling around, and if you look here, and as they look at the effects of that bang, as it did something to the superstructure, undercarriage, or the part of the wing. And you repair it, and you learn from it, and you live to fight another day, I guess, in that particular case. What else do we have? We've got volume on this as well. Again, planes with lift, we're talking about external flows. In this case, static air and the plane flying through it. You'll see the vortices trailing off the wings in this. I think it's a 757. 757s were actually planes that have very high lift attached to them. And I remember there was an incident, maybe at Orange County or maybe LAX airports, where a small private jet landing behind one of these 757s was actually just beaten into the ground by the vortices that roll off the wings, which are, because we think about an airfoil as being a plane structure, but of course it can move. Any circulation you have on the wing can actually move along the length of the wing and kind of drip off the tips of the wings, which is why you sometimes see these fins on the side to stop those vortices shedding off. And in this particular case, it slammed a private jet into the ground that was landing too close behind it. So they changed the landing scheduling after that to stop things like that happening. Okay. Obviously a bad thing, right? If you're in the plane that it follows behind. This is, the music's on there, but I won't have it talking over me. This is Felix Baumgartner trying to do the highest, I don't know if it's highest parachute jump or the highest wingsuit jump. So he goes up in this, with this helium balloon up into the stratosphere, I guess, where you can actually see the curvature of the Earth. Not sure exactly what the height is, maybe certainly higher than commercial planes, so it's 50, 60, 70,000 feet, I think. And then jumps out of there with oxygen and quite spectacular. So you can see I have no idea how high that is, but certainly it's much higher than commercial planes, because you see the curvature of the Earth at that height. And a free fall, I guess it's not a wingsuit, or maybe it is. A bit of a tumble. Not sure how controlled that is. Well, you're not sure. He looks like he's set now. Yeah, well, it's a parachute drop. And he lives also to tell the tale. Well, we'll see if Red Bull actually take that off or contest that when I post that on my own YouTube. Iron Man, nah, I don't want to do it. And so the more mundane things as well would be, well, actually this is, I'm not sure what this is. Very jazzy. Oh yeah, so this is, one way actually to measure the size distribution of particles in soils is to look at the rates at which they settle. Big particles settle quickly, as we can talk about today, and we can calculate that based on coefficient of drag and their mass, and fine particles settle more slowly. So if you track the rate at which particles settle, you can say something about the size distribution of soils. And one standard way of doing gradation on them, finding out what that gradation is to be able to look at the rate at which they settle. And that's because when you look at very fine fractions, it's tough to be able to get a sieve which is fine enough to be able to exclude and subdivide those fine fractions. And that's also why when you look at geological sequences, there's usually this fining upward sequence because the deposition takes a finite amount of time. And so if you look at estuaries and look at the distribution of particle size in estuary, close to land it's typically quite granular. Say the Mississippi fan as it goes off from New Orleans into the Gulf of Mexico. If you go further off there, the soils happen to be much more clay-like because it's finer particles that can travel further before they settle out onto the seabed. And finally, this is a modeling exercise for simulation of double diffusion, so gravitational density settling of a drop going into water and splitting up into multiple droplets, then splitting up into multiple droplets, diffusing at the same time. It's actually quite beautiful in its own way, and it's being affected where maybe the density of the droplet is only slightly different from the density of the carrier fluid which it's in, or the static carrier fluid, and the patterns you get are because the droplet affects the circulation of the static fluid, which feeds back into the circulation of the droplet, and you get these rather interesting patterns developing. But it's all related to external flows. An object could be a grain of sand, could be Felix Baumgartner dropping through air, or water, some fluid anyway, and the resulting patterns being controlled by that. So that's kind of where perhaps we'll mess around with today. So that's kind of the introductory material for what we'll talk about today. And so it will, I know you'll be sad, be our last time together this semester, I think. We'll kind of close out external flows by talking about some of the features that are left to talk about. And so the main point today is we'll talk about one of the things we'd like to be able to do, what's terminal velocity for Felix Baumgartner as he drops through the atmosphere. And so evaluating motion is one thing we'd like to do. Composite drag, we talked a little bit about already, just means that some drag is due to destroying momentum of the fluid against a body, and the other one is due to viscosity, and they play their role at different times. And of course lift is just the corollary of drag in that it's really the same procedures, and what we'll find out that we need to do is we need to be able to evaluate forces on structures. And so maybe as usual we'll talk a little bit just to orient ourselves. We made this big point last time, and I can draw this curve just as easily as you've seen it many times. It's our Moody-esque curve for Reynolds number, which is always defined in the same way: a characteristic dimension, density, and a viscosity, and what we've called either coefficient of drag or coefficient of lift. And our stylized way of looking at them is relative to Reynolds number, where this Reynolds number may be something like 10 to the 3-ish, and that this zone is laminar, this zone is turbulent, so the patterns that we get around structures, which we've also drawn a number of times, it's sort of the same structure, is that in laminar flow it kind of hugs the body from one side to the other, and that's just the geometry of the flow. For turbulent flow it hugs the body, but there's some kind of separation on the back side that gives you this turbulent wake. And even though the turbulent wake changes and sometimes will shed vortices at different magnitudes, it's essentially the same in that the flow regime, even though it might reorganize slightly, the drag coefficient or the lift coefficient, drag in this particular case, is something that really doesn't change as you change the Reynolds number. And so we can imagine that if you look at the role of pressure drag versus viscous drag, then in this case this is typically a function of Reynolds number. So this drag coefficient, as we'll see, is equal to some constant divided by Reynolds number, typically. CONST, that's not very well written, but you can see that. And so because this, as we'll look at this later, you can see that viscosity plays a role in this. So in other words, the coefficient of drag here is some function of Reynolds number for sure, right? Because we've said this. Some function of viscosity. And it's not a function of roughness. Do this. And conversely, if we look at the coefficient of drag in this region, this is flat, so it's clearly not a function of Reynolds number. So Reynolds number not. Viscosity not either, as it'll turn out, but density yes, and also it's a function of relative roughness. And so you can imagine that either you might have different curves stacked at different heights, or actually the bigger effect of roughness, as we'll see, is that this roughness controls this transition. So if you like, laminar to turbulent transition is controlled by the roughness. And so that's, I'm not sure why I'm putting that afterwards. And so if you look at a golf balls could be smooth or they could be dimpled. The reason they're dimpled is that roughness makes this transition for laminar to turbulent occur at lower Reynolds numbers, lower velocities when you're hitting it, so you don't have to hit it hard as you would do to be able to get it to travel in the turbulent regime. And it turns out that kind of counterintuitively, even though this is turbulent and there's lots of dissipation of energy in the fluid, it's actually more effective to the drag coefficient is effectively lower at higher Reynolds numbers because the viscous drag is removed from the system. So I started doing this here before. So pressure drag is important in the turbulent regime, where viscosity is not important, this term here. And conversely to this, viscous drag is important in the laminar regime, and turbulent pressure drag is less important because all the losses are viscous. And so that's just kind of setting the stage for this. The other thing that we will look at, and we could look at, and this is really the curve that I've drawn above. You can see that it's not quite true what I've said about it, and that is that it's not really just a straight line and then a horizontal line, but if you idealize it, you could imagine that that's the case. And this happens to be the drag coefficient for a sphere falling through a viscous fluid in laminar flow. You see that there's a line that it departs from, and there's a departure from that and it changes the Reynolds number. This would be our 10 to the 3, and you see that kind of to the right of that it's kind of horizontal, and to the left of this it's kind of inclined. They don't quite meet up, so it's not quite as ideal as I've drawn it, but certainly we can characterize it in terms of these main dependencies. The other thing that we did, which we did last time, which is actually useful to revisit maybe, was this. You remember that we messed around with the idea that we could take an airfoil, and this was the modeling thing that I used the video for, and we could measure the drag on this airfoil, or lift if you wanted to. It just happens that we did drag. And if we plotted the magnitude of the drag coefficient, and that drag coefficient was the drag force, density of air, 1 kilogram per cubic meter, velocity is 1 meter a second, and the cross-sectional area of the wing. Probably we wouldn't use the planiform area of the wing, we'd probably use the vertical frontal area. But regardless, this drag coefficient I think was 1300 here, it was 130 here, and it was 13 here. And then it was maybe then it was maybe 5 or something. And these different Reynolds numbers. And so if you look at this is a Reynolds number of 1, And so the fact that this exists here at 1 means that the equation of this curve has to be, and it changed for each order of magnitude change in Reynolds number, this also changed by 1 order of magnitude, so it's proportional to 1 over r. And so the corresponding drag coefficient here is actually equal to 13 over Reynolds number, as we define this. And actually it's off by the fact that we ignored this half in here. So if we put in this half to calculate that, it would turn this actually into 26 over Reynolds number. And I think that's just a coincidence, but it shows you at least that we had this. I'll separate from this. But it shows at least it's a linear function of 1 over Reynolds number. There's a function of 1 over Reynolds number in this regime, and there's some coefficient attached to it. By luck, maybe, more than judgment, it ended up being in the ballpark of what we think that should be, but that's basically an exposition of how we might get these curves. We happen to do it by measuring forces on a virtual airfoil. You could also measure it in a wind tunnel on a real airfoil that was just scaled down to whatever the dimensions were that you thought were appropriate. And so if you look at trying to reconcile that with this, then this is exactly the expression that we are talking about. And we were, as we saw here, we weren't very far off from this. And it also changes clearly as a function of Reynolds number. And I guess in our particular case, the transition to changing from this dependency on Reynolds number was around the number I took, right? So it's actually 10 to the 0, so it's here. So it's much earlier than this. So who knows whether that was very accurate or not, but it gives you the idea of actually where those might come from. And so you can imagine that for a whole bunch of different shapes, every shape that you can imagine, if you want to do the calculations that we'll talk about today, is we'd like to know what the forces are on an object, because everything that we do revolves around those forces. When I drop this, it's a balance of forces between gravity acting on this, and it'll fall to the floor because it will accelerate because of Newton's second law. A parachute slows down to some terminal velocity because the force, the weight of the person on it versus the drag that's pushing up against it counter each other. They're in exact balance, and therefore by equating those forces we can actually say what the velocity would be. We can solve for the velocity. And so long as we can calculate what the drag coefficient would be or the lift coefficient would be for a given geometry, we can use that to be able to calculate those velocities. And you can imagine that they change with different features. So you can imagine it for a section of an oval as it gets progressively longer. So in other words, it gets progressively longer in this direction. And obviously as it gets progressively longer, you'd expect it to asymptote to some steady value. You can look at the drag on a wing and get that. Again, you can imagine as a function of the inclination of that, the drag would be more as it's less like an airfoil and more like pushing air on a plate. You can look at the drag around different objects, a small cylinder in this case, and a much bigger cylinder that has an elongate tail to it to be able to try and reduce the vortices that get shed at the back of this, and to have a much thinner boundary layer around this, and to improve aerodynamics, and to look at the behavior of different structures. A flat plate, a cylinder, and typically these are functions of a chosen Reynolds number that's defined. So you can either plot it in the way that we did before as a function of Reynolds number for simple geometry, such as a sphere or a cylinder, or you can plot it as a function of a single Reynolds number and some feature of the geometry of these cases. So in this case, the geometry is one where the length of the cylinder is increasing, the B dimension is increasing relative to the height or the diameter of the cylinder, and it's just a matter of reading off for the appropriate geometry that you have the magnitude of the drag coefficient and making sure that you're at the right Reynolds number for what your flow is. And so that's exactly the approach that we'll use in a second if I don't talk too long to get there. For laminar flows, we've already seen that for spheres, it's given as a function of Reynolds number and a constant. If you change the geometry of the body, then the magnitude of that coefficient changes. Not very much, you see. But it has to be, in this case, these would all be for magnitudes of laminar flow in that initial portion of our system. Okay. So, all right. So the most important thing we need to do is to be able to take what we have now and talk about evaluating motion. And the easiest way for us to discuss that is to talk about a couple of examples that are in here. I won't use these examples, but there are two examples. One is for the Stokes settling, dropping a grain of sand within water and looking at the rate at which it settles, which is laminar. And the other one is dealing with how big can a hailstone get to be if it's lofted up in the updrafts of a cloud, where its rate of descent is static if the updrafts provide enough drag on it that directly counters the mass of the hailstone. It'll just be lofted into the cloud, and it will be able to be plated with ice to get larger and larger and larger. So I guess the question is asking, what's the largest hailstone you can develop in a cloud for a given velocity of upflow? And so it's easier to come back to this and talk about these because they exist in two different regimes. And the basic idea is that we're balancing forces. And the balancing of the forces would be that if you take a sphere, we're taking the weight of that sphere, which is its mass times g, and we're applying to this a couple of forces. One would be a buoyant force, which we know would be equal to the unit weight of the fluid multiplied by the volume of the thing. So this is also the same as volume times rho g. And our new addition to this, which is due to the forces which are applied around this, and this is what we've called uppercase curly D, right, to make a drag force. And so the other force which is acting on this is also an equivalent drag force, which is acting upwards. And so we can use Newton's second law, which is F equals ma, or sum of forces. We're on here, right? In the easiest way, if there's equilibrium, there's no accelerations. And so in this particular case, it would merely be that W minus buoyant force, which may be trivial, is equal to curly D, drag coefficient. That's it. Just by equating forces. And so long as we can get this, certainly if we know the volume and its density and what planet we're on, for gravity we know this, certainly this for air is going to be trivial and can probably neglect it. For water, maybe not. And so long as we can calculate the drag force. And so intrinsically, we know what the drag force is because we know this. And so if we know the drag coefficient, then we can presumably calculate this. And then the one free term that's going to exist is going to be the velocity, either velocity squared or velocity. And so that's where it matters whether we're dealing with a laminar case. So I'm going to split this here and go off in these. No, actually, I'm not going to do that. So if we talk about laminar. So you agree, I hope, that we can certainly get the right-hand side here. Let's ignore buoyant forces. So if we write the drag force, it's going to be equal to, I'll write at the bottom so you can see both at the same time. It's going to be equal to the coefficient of drag multiplied by a half times the density of the fluid times the velocity squared times the area. of the system. And this is going to be equal to W, for instance, W minus FB. And so we know this, but this equation, I guess, would do for both of these. It'll do both for laminar and turbulent, but specifically for the laminar case, this coefficient of drag is going to be a function of some constant over Reynolds number. And that for us is going to be equal to some constant over Reynolds number, which we write out in longhand is density, velocity, and a characteristic dimension. Let's use not d, 2 times radius, just because it's not confusing, and viscosity. And so if we substitute this term into this expression here and write out curly d, it's going to be equal to some constant, which we will know, 24 for a sphere, right? Density, velocity, 2 times radius, and viscosity. There's a half in there, and it'll be a density, a velocity squared, and an area which will be 2 pi r squared. And if we get rid of the terms that we do and need and don't need, we get rid of the densities, will drop out. We said before that laminar behavior is not a function of density. We have a velocity on the bottom, which will drop out. And we'll end up with, if we rearrange this, we'd end up with the velocity being equal to the weight minus the buoyant force, which is this. And it's going to be equal to, it's going to get messy, isn't it? 2 times the radius times 2 divided by a constant, a viscosity, and 2 pi r squared. But importantly, you see that this ends up being a function of velocity, which we can now determine. We know what the weight of the thing is, buoyant weight. We know what the geometry of our sphere is. We know what the viscosity of the fluid flowing around it is, and that's what provides the drag to it. And so directly from that, we can calculate exactly what this is. So it'll be different from any particular problem we try and solve, but that's basically the message. If we look in, and we've proven to ourselves that it's a function of viscosity, and so in this particular case, the velocity is a function of the viscosity. It's all viscous drag that's being applied to the system. If we go to the right side of here, and we write this same equation, then all that's going to change now is that the coefficient of drag is just equal to constant. And so now, when we write out this expression, we're going to end up with, this is again going to be weight minus buoyant force. So weight minus buoyant force, which we know, is going to be equal to some constant times a half density of the fluid, velocity squared, times the area of the sphere. It's the planiform area. Looking at the sphere, it's the area that you see, so it's pi d squared upon 4. And the only thing that we don't know in this is going to be the velocity. And so we can rearrange this for W minus FB. And we're going to divide through by a constant times a half times the density of the fluid times the cross-sectional area. And this is going to be V squared. And if we do that to both sides, then we have it. Yeah, go ahead. How long's your hand been up, by the way?
Like a minute.
Okay. That's good.
What does the 2R2 stand for again? In the,
Two,
in
two,
the
two.
laminar? What's the right next to the
Two are this one.
Yeah.
This is the diameter. So this was Reynolds number. So Reynolds number is a density, a velocity, and a characteristic length, diameter. I just chose to. This is D, but I didn't want to use D because we're using squiggly D here. Yeah. So this is diameter. So that's it. So there are two different ways of solving, and it depends on what regime you are. It's a bit like pipe flow, and it matters whether you're in the regime where the drag coefficient is inversely proportional to Reynolds number, because the equation you get out of it gives you directly a velocity as a function of the other terms you have. And if you're in the turbulent regime, because the drag coefficient is constant, then the magnitude of the velocity you get out ends up being a velocity squared, because you don't factor Reynolds number into this, and the Reynolds number gives you an extra velocity that cancels out with the velocity squared term in this drag coefficient. It's physically what's going on. So those are the two essential ways to be able to solve these problems. I didn't go through this you can see from these two examples, one is laminar and one is turbulent and does that. The other thing that we didn't talk about, but maybe is worthwhile mentioning, is that if you look at this graph, which divides up these two regimes, the regimes exist because the flow regimes are different as you go from A to B to C to D, which are each of these in progression, A, B, C, D. So this is exactly the one that we talked about in terms of the Tacoma Narrows Bridge. This is the bridge deck that sits here. And the wind blowing over the top of it, first of all, sheds off a vortex. This gets carried downstream, and it then sheds off another one. And so at any snap in time, this is the most recently produced one. This was produced a little while before, a little while before, a little while before. And so this alternate pinging from top to bottom means that the frequency of these are shed. And this is the equation that I wrote is in the notes earlier on, but I wrote it down below this. It's this here. Is equal to 1 minus 20 over Reynolds number, and for a particular range of Reynolds numbers. And so Reynolds number would be some characteristic dimension. It'd be the diameter, right? D would be the diameter for the Reynolds number here. Velocity, density, diameter over viscosity, right? So this is some characteristic length. But this allows you to calculate the frequency of the shedding of the vortices. So that if that frequency happens to be the resonant frequency that the bridge would ring at, or the guitar string would ring at when you ping it, then it's a reinforcing feedback that just adds to the motion of the bridge. You can check the dimensional homogeneity of this. Reynolds number is non-dimensional, as it has to be. Velocity is meters per second, and diameter is meters, and so the units have to be a frequency, right? 1 over seconds. And so it's the frequency at which this is excited. And so if you wanted to, you could calculate exactly the frequency of the bridge that you didn't want to build it as the resonant frequency if you knew something about the wind speeds you expected, what the fluids were, air, and its viscosities and densities, which are well defined, and also the characteristic dimension of the bridge. Okay, that's just as a side. So probably the most important part is knowing how to calculate the velocities of some of these things. We talked about surface roughness and the fact that in these different regimes, for a smooth sphere, smooth means no roughness, but the role of roughness, if you only have one curve that represents the coefficient of drag or lift, then clearly roughness doesn't matter very much. But as I mentioned before, what matters is the location of this transition for laminar to turbulent is in some way conditioned by the magnitude of roughness. And so this transition will actually occur earlier for rougher balls. So if you have a rough ball, then the transition from laminar to turbulent flow is potentially advanced at an earlier Reynolds number. And because Reynolds number is proportional to velocity, it means it goes turbulent at a lower velocity. And so this is the reason why golf balls are dimpled, is that if you look at the behavior for the coefficient of drag for a smooth sphere, so I guess we're looking at this zone here, around this zone here, where you get this little dip in behavior because of the boundary layers. What happens, I think, is that the boundary layer, the wake becomes narrower and more organized, and this narrow turbulent wake is the reason why all of a sudden at E you get this drop, because the flow regime is just optimized to be super efficient for flow, that the losses are viscous because this wake now is not as wide as it was in the lee of this ball. And if you look at that in this figure here, then this is saying that this drop that comes down, if it's a smooth ball, it happens to be at this Reynolds number. If it's a rough ball, then all of a sudden this drop occurs at a much lower Reynolds number, almost 10 times lower. And so it means that to make it a turbulent flow around a dimpled golf ball, it only has to be traveling at a tenth of the speed as it does if it's a smooth ball for it to benefit from this trough in the coefficient of drag. Low coefficient of drag means that the drag force, right, CD is equal to D over a half rho V squared A. So the drag force is proportional to the coefficient of drag. So reducing this coefficient of drag from this magnitude to some smaller magnitude, even though now it's not quite as small as this, it happens much earlier. And so it benefits it. So I don't like golf myself, but never quite understood why people play golf. But I could be preaching to the converted here, but there's never been something that I've played it, but I've never quite understood it. Anyway, so all right, so that's that. If we look at maybe the final things that we need to talk about, lift. Well, lift I think is no different from drag. It's really a balance of looking at forces on objects, and so we can maybe talk about that briefly. But it's basically the same idea. If you know what your flow regime is around an airfoil, yeah, well, fine. No, forget that. Let me talk about composite drag first. So the other thing is, you can imagine that you could have objects that are put in airstreams that are not just a single sphere, but are a sphere plus something else. And a classic idea of that would be something like a wind tower. And so there's no reason why you can't, in that particular case, calculate the drag coefficient that you have for the sphere that exists at the top of the wind tower, and the drag that you get for the cylinder that exists below it, to calculate both of those magnitudes of forces, and then you apply those forces at the right locations. On the cylinder, it would be at half height, right? It would be kind of the centroid of the distribution. On the sphere, it would be at half height of the sphere. And then you can resolve forces to see what kind of moment you have to apply to this to be able to keep it up. And so if you wanted to calculate moments, I guess you'd come up with this length here, L sphere, so D sphere times L sphere plus D, the force on the cylinder, times the force on the cylinder, has to equal the moment that's applied, resisted by this. Weight wouldn't matter in this particular case because it's resolved through the moment of action of that moment, but you can just resolve forces. And so there's no reason why we need to limit ourselves only to one shape, if you like, one airfoil or one sphere, but we can add the effects together. And of course, if you want to do that, you can do that for the drag on a car by looking at the front end, the windshield, the roof, the lower rear end, the side of the car, etc. And you can sum all these components so that you get a summation of all the drag forces on the system, and so you end up with a composite drag which represents the behavior of the system. So I think that's straightforward as well. So, and you can get drag for all the weird and wonderful things you could ever imagine. You can get it for a flag that's fluttering in the wind. It has to be for a specific Reynolds number. Presumably, since there's a single value that's given, it's probably in the turbulent regime, which it probably is with air because of its low viscosity. For a parachute as well, you're probably turbulent as well because it's usually used in air. You could use it in water, but it's usually used in air where the viscosity is low. And so you can end up using tables for these to get even drag for a dolphin, for God's sake, or birds, which kind of makes sense. So that's drag. I think lift is really no different in that you like to be able to figure out exactly what the forces are that are applied on the structure. And it really revolves around the idea of being able to use, again, a chart that gives you coefficient lift at a particular Reynolds number. Is that in this case? For different geometries of an airfoil, you have different coefficients of lift. And for those different coefficients of lift, in this particular case, this is plotted against drag. I guess these must be for a single Reynolds number. But you'd have, in this particular case, two forces that you could calculate. Curly D, which would come from coefficient of drag, is equal to curly D divided by half rho V squared A. And there'd be a particular A that you'd have to worry about. I guess you should be wary of what the A is, right? Because A could be the planiform area as you're looking down on a wing, or it could be the planiform area as you're looking at the front of the wing. So you need to know exactly what that is. And you could calculate from the... Well, it keeps on wanting to do that once in a while. Don't need to see that. And the coefficient of squiggly L, which is equal to lift, again, a half rho V squared A. And again, it matters what this is. It certainly makes sense for lift that it's the area of the looking down on the airfoil, right? The planiform area, not the frontal area. And you have a magnitude of a squiggly lift that's attached to this. And you can do exactly the same things as we did before. If you know that the plane weighs 20 tons, then you need an amount of lift to be able to lift that up. And so you could be able to calculate what the velocity is that you have to get on the runway so it equals the weight of the plane to be able to lift it. And so it's the same calculation. And so the other, I think, fun thing with this as well, which you can think about, is rotating objects. And that's the last thing that we'll talk about. And so you know that when you're playing table tennis, if you chop the ball, it kind of spins upwards and stops in the air on the table and drops down on the table because it's got backspin on it. And it's got backspin on it, and what it means is it tries to go upwards. And so it's the same as spin on a baseball. And that is, if you imagine a ball which is spinning, you can get the flow regime around that ball by adding two solutions. One is a solution for a ball that's not spinning, where the viscous flow around it looks like this, and one where the ball is not moving but is only spinning, in which case it's dragging the flow around with it. The velocity of rotation here is the same velocity of the air it carries with it, and if it goes to infinity, it goes back to zero velocity a long way away. So if you add these two together, you actually end with a circulation pattern like this, which is a bit like an airfoil, right? The air comes in here, it splits, part of it goes over the top, which has a long flow path, but it ends up at this point, and part of it goes over the bottom and has a short flow path. But if they both meet up there with the same molecules of air, then clearly this one has gone faster over the top than this one. And if it's gone faster, then Bernoulli says that there's some lift to it. And so what it's physically doing is it's providing lift to this ball to make it go up in the air. And that's the reason why if you put backspin on something, it tends to lift. It stalls in the air. Instead of dropping down to the table tennis table on the other side, it hangs in the air and then stalls and then falls. And so there's an example in here which I think is a cool example that basically says if you want to make a table tennis ball go horizontally and never drop, what do you do to it? Well, if you put backspin on it, it gets some lift to it. And if you look at the forces which are applied to this, then you have the weight acting downwards, and you have the lift acting upwards. And if those two are exactly the same as each other, then it doesn't fall, in theory. Obviously, it loses its spin at some time, but at some stage, if you put enough rotation on it, you can stop it from dropping out of the air. And so anyway, so that's, we did actually get through the things I wanted to get to. And so that's it. I know we're kind of out of time, and I don't really have much more to say, but I will kind of go back to this view of big picture things that may be useful to you in thinking about this. Is that in this last part of the class, the recipe part of the class, where we talk about pipe flows, external flows, which we just finished, and then open channel flows in week 13, is that they actually are the same to each other. They're flows where the Reynolds number says exactly what the flow regime looks like, whether in a pipe or around a sphere or in a channel. And if that is satisfied, we can calculate the forces that result from that. For pipe flow, it's the force that resists its flow, the friction, which we want to know to calculate the velocity. External flows, it may be the force we want to calculate to see how much lift we get on an airfoil, but it's the same thing. And again, it depends on the regime, laminar or turbulent. And when we talk about open channel flow after Thanksgiving, then it's the same thing as well. It's a drag that's applied on the flow that occurs as it goes down the channel, and that conditions how quickly it can go. If the force is a finite force, the only way we can overcome that is by making the channel steeper, so that the downstream force driving the flow is larger now than that which is resisting it, and it readjusts so that the velocity goes up, and then the system is back in balance again. But there's really not much difference between those different things that we'll do. So that's the essence of what we'll do.